So for part 2 of problem 4, you asked us to create a brief video demonstrating and explaining why my solution in part 1 of problem 4 holds regardless of the position of P. And so for my construction, I just have this parallelogram ABCD and this arbitrary point P, which can be placed anywhere inside the parallelogram. So I'm just going to go ahead and place it here. And I'm going to go ahead and construct a line parallel to AB going through point P. And I will be able to do that through proposition 3.1.4. And so I'm going to go ahead and construct that now. So there you go. And I'm going to go ahead and mark the intersection points here. And I'm going to go ahead and construct the triangle ABP and the triangle CDP. And so what we're going to observe is that since FG is constructed to be parallel to AB, then it'll also be parallel to DC, and that'll be through proposition 3.1.3. And then we're going to also notice that this triangle, well, first we're going to establish that ABGF is itself a parallelogram. And by construction, we have that AB is parallel to FG. And since AD is parallel to BC, then we're going to have that AF is parallel to BG. Similarly, we're going to say that FGCD is also a parallelogram. We already established that FG is parallel to DC. And so all that's left is to observe that DF must be parallel to CG, again, because AD is parallel to BC. And that's because ABCD is given to be a parallelogram. And so we're going to notice that the triangle ABP, so that'll be this one here. This triangle here, ABP, has half the area of the parallelogram ABGF, and that's through proposition 3.2.10 that says that if a triangle and a parallelogram have the same base and are within the same parallels, then the triangle has half the area of the parallelogram. Similarly, this triangle here, DPC, is going to have half the area of the parallelogram FGCD. And so when we go to add up these two areas, so the total area of the parallelogram ABCD is going to be contained by the two parallelograms ABGF and FGCD. So each triangle here represents half the area of each smaller parallelogram. So when we go to add up the area of the two triangles ABP and CDP, we're going to get that the sum of these two triangles is going to be half of the entire thing, because each triangle represents half of its respective parallelogram. And that'll hold for any, no matter where we put P, because the line FG will always be parallel to both AB and CD, so the argument won't change. And the line AF will always be parallel to BG, and CG will always be parallel to DF. And so no matter where we place this point here, P, the argument will hold, and the sum of these two triangles will be half the area of the parallelogram, or the parallelogram. In other words, the parallelogram will have twice the area of the sum of these two triangles.